Bisection method for solving nonlinear equations. The given equation is x cubic minus x minus 2 equals 0. We need to find an initial interval AB such that FA and FB have opposite signs, so that f of A times f of B is less than 0. This ensures that a root exists between A and B. Evaluate the function at the interval endpoints. Let's evaluate the function at some points to find the interval. Since f1 is less than 0 and f2 is greater than 0, we can choose the initial interval as 1 and 2. Calculate the midpoint and evaluate the function. The midpoint of the interval 1 and 2 is Update the interval. Since f1 is less than 0 and f1.5 is greater than 0, but f1.5 is closer to 0 than f1, we update the interval to 1.5 and 2. Repeat the process. The midpoint of the interval, 1.5 and 2, is Update the interval again. Since f1.5 is less than 0 and f1.75 is greater than 0, we update the interval to 1.5 and 1.75. Continue iterating. We continue this process until the interval is small enough, or the function value at the midpoint is close enough to 0. After several iterations, we find that the root of the equation x cubic minus x minus 2 equals 0 is approximately. X is approximately to 1.5213427. This value can be refined further by continuing the iterations. Design of a suspension bridge. The bisection method can be used in the design of a suspension bridge to determine the optimal sag of the main cables. Problem statement. The main cables of a suspension bridge are suspended between two towers, and their shape can be modeled using a catenary curve. The sag of the cables is critical to ensure the structural integrity and stability of the bridge. Mathematical model. The catenary curve can be described by the equation.
Where A and C are constants that depend on the tension in the cables and the distance between the towers.
Nonlinear equation. The sag of the cables can be determined by solving a nonlinear equation of the form.
Where delta is the desired sag of the cables.
Bisection method application. The bisection method can be used to solve this nonlinear equation and determine the optimal sag of the cables. By iteratively refining the interval, the method can converge to the solution, ensuring that the cables are designed with the correct sag to withstand various loads and stresses. Practical significance. Accurate calculation of the sag is crucial to ensure the safety and durability of the bridge. A small error in the sag can lead to significant stresses and potentially catastrophic failures. The bisection method provides a reliable and efficient way to solve this nonlinear equation, making it an essential tool in the design of suspension bridges.
Thank you for watching. Like, share and subscribe.